Alright, so in this tutorial we're going to pick up from our scenarios and define work, apply this definition to the scenarios and determine who did and did not do work, and then we're going to generalize it into an equation and then some problem solving. There's a lot of nitpicking here, so pay close attention to the details. Once you get it, it's fairly straightforward. Alright, so we had the four situations. We had someone pushing a car, Becky, we had Michelle lifting, carrying books up the stairs, we had Trav lifting barbells, and then Tim pulling things around. So before we answer who does the most work, let's define what work is. And let's keep in mind, work in the everyday sense means a lot of different things to different people. In physics, it has a very specific meaning, and we're going to talk about why that specific meaning is so important. It's not just defining something for the sake of it. It gives us some very important insight about nature and a different way of looking at changes in nature. Okay, so by definition, work is a force applied to something. Okay, and it's not just a force applied, it's a force applied over some distance. Okay, so there's two components to doing work. You have to apply a force, and the object has to move in response to that force. So holding something isn't doing work, even though there's a force. An object rolling across the ground, even though it's moving, if there's no force acting on it, then there's no work. So the combination of both is really important. Now, here where some nuances come in. Well, actually, before we get to that, so since there has to be some distance, we can rule out Becky as doing work. So we can say Becky does no work on the car. Now, we got to be specific about the object that work is being done on, because there's simply no change in position. Okay, so you'll often see a simple problem like that. If I hold a bowling ball for 10 minutes, I'm technically not doing any work on it if I'm keeping it at the same level. Now, at the muscular level, my muscles are doing work because they are exerting a force to hold my arm up, and they are actually contracting over a microscopic distance. And that's why you'll eventually get tired, even though you're not doing any work, technically speaking. Okay, the next aspect of work, where the force is in the same direction, okay, as the distance. That's a really, really important criterion. So if I represent a force with a vector like this, then whatever distance we have has to be in that same general direction. It can also be opposite direction as well. That's why I put the word direction in quotes. It just can't be perpendicular to it, and we'll see instances of that. So does that help us rule out any of the situations there? And I'm trying to think about it, and the answer is yes. We can rule out Tim. Okay, Tim does very little work. He technically does some, but essentially zero. On his backpack now. Why? Because the direction of the force is essentially, if this is Tim, okay, and here's his backpack, the force he has to exert on it to hold it up is upward, okay? But the backpack is moving this way. So technically there's not any work being done. You might argue, well, isn't he pulling the backpack forward? Well, initially he is when he first starts moving, but once he's walking at a constant speed, the backpack wants to keep moving in a constant speed anyway. The shoulders hold the backpack up, preventing him from falling, but they do not pull the backpack forward. So the shoulders will only come into play when he starts and stops. So in this scenario, he does that a little bit, but not a whole lot. Okay, so that's a subtle little point. Now, next thing about that is distance is technically the displacement in the direction of the force. Okay, and this is the hardest one really to understand. Essentially, it's this. Imagine that I lift a bowling ball up. I'm exerting a force up. I'm just going to draw the schematically over here, right? The force is up, and the bowling ball is displaced up. Now let's say, rather than dropping it, I lower the bowling ball with my hands. So as I'm lowering it, I'm still lifting up on it, but the displacement is now down. So if I set it back where I started, then the overall displacement in that line of action, the up and down, is zero. So technically no work has been done on the bowling ball. So going back to our situations, that would rule out Trav. We could argue that Trav does no work on the barbells because the displacement is 0. Okay, we're going to have to investigate that a little bit more, but just to kind of give you another way of approaching it, we can say when the force and direction are in the same direction, when the force and distance are in the same direction, then we have positive work. And then if our force and distance are in opposite directions, then we have negative work. And so if we combine both of those in that situation, since the distances are the same and the forces are the same, they will add up to 0. So that leaves with Michelle. Did she do any work on those 2 books? Does that situation meet the criteria that we've laid out here? So take a look at that carefully and think about it and decide if she did indeed do work. Okay, well, hopefully you realize that when she was walking down the hallway, she wasn't really doing any work on the books. That's kind of like the Tim situation. Holding them up at the constant height was not doing any work on them. That's kind of like the Becky situation. Again, it's kind of like the Tim. However, she did go from the first floor to the second floor. And if she went from the first floor to the second floor, she had to lift the books and herself as she went up the stairs. And since it never said she came back down, it would not be like the barbell situation. So we would say Michelle did work on her books and herself because, well, the simplest way of answering that is they were lifted up. And we're going to see, anytime you lift something up without bringing it back down, you're going to be doing work on it. That has important consequences. So as I said earlier, this might seem like a lot of nitpicking. Why are we going through great lengths to define work as a force over distance and give it these particular stipulations? Well, here's the payoff to it. This actually leads to one of the grandest ideas, not only in physics, but all science. Okay? Work is a process. Kind of like impulse. Remember, impulse is a force acting over time. Here we're looking at a force acting over distance. And when we talk about an impulse, we said we get an equivalent change in momentum. So that would seem to lead that force over distance would lead to a similar type of change. And what's that change in nature? Well, it's nature's way of converting energy. There's the big word. That's the big idea. Energy from one form to another. Okay, so this is our, whoops, I spelled that wrong. Excuse me. This is our, really spelled that wrong, roundabout way of introducing a concept that you've heard about since you've really started taking science, this idea of energy. And now looking at how energy is converted, transformed, changed. You've learned about solar energy, sound energy, light energy, heat energy, kinetic energy, potential energy, chemical energy, electrical energy. They are found through all the different sciences. You've also learned that you cannot create nor destroy energy. While that is 99% true for most of the things you talk about, what can happen is you can take energy from one form to another. I can take fuel, burn it, release the inherent chemical potential energy to get thermal energy or light energy. I can pedal my bike to get kinetic energy by taking chemical energy from stores in my body. Okay? So energy, we'll have much more to say about it, is so important because without it, nothing could ever change. Okay? Anything that changes in nature is an energy change of some form or another. And if there's an energy change, work must be done at some level. What does that mean? There must be a force and a distance over which that force is acting. That's why work is a very powerful and important concept. Okay, so let's turn to the mathematics of this. The equation for work is pretty straightforward. It's simply equal to force times the dot product of a distance. Okay? And that dot product here is important. That means, remember, F and D have to be in the same direction, or the components have to match up. We'll see that later. The units for work based on this are nothing more than newtons times meters. Not to be confused with Newton second. This is called a joule, capital J. You may recall joules from chemistry. Those are units of energy, and that's not a coincidence. If work is a process by which we get an equivalent change of energy, then the units will ultimately be the same. And what makes work really useful, especially compared to momentum, is that it is scalar. There is no direction associated with overall work. We don't say you do 10 joules of work east or south or up or down. It's simply scalar. So any combinations of work you have, you can add them very, very nicely. All right, so let's do a quick problem or two. So we got a cat falls from a tree that's 6 meters tall. How much work was done on the cat? All right, well, if we're going to figure out how much work is done on the cat, we have to establish what force was acting on it and what was the distance. So when it falls, it's pretty obvious that the force on it is gravity. Okay, and the magnitude is simply mg. And so if we take 3.5, and I'm going to call G10 here, we have 35 newtons of force. Okay, what's the relevant distance? Well, if the cat is being forced this way, I need a distance at that way, and that's, of course, the height of the tree, 6.0 meters. So the work done is simply equal to 6.0 meters times 35 newtons. That's 210 newton meters, or 210 joules. Okay, that's a pretty straightforward problem. You know, one thing that's not obvious about that is what's the force, but you could reason that out just as we did there. Okay, now why do we care that 210 joules of work was done on it? Because it changed something about the cat. What did it change? And we'll do this in more detail, but it changed the potential energy. Well, the energy the cat had stored by being up in the tree to kinetic energy, energy of motion. Okay, that cat is moving just before it hits the ground, and that energy can do quite a bit of damage to the cat or to something that it falls upon. And so we want to keep that in mind for future problems, not necessarily for a cat, but just collisions in general. All right, another generic type problem. I have two vectors, 10 newtons acting to the east, and then acting south. For the first part, it goes 4 meters, and then for the second part, it goes 3 meters. Now I want to know ultimately how much overall work was done on that object. Okay? So we just take it into, we don't do the whole thing at once, we take it into parts. All right? So our first part is the eastward part. What's our force? Well, that's 10 newtons. What's the relevant distance? 4 meters. So the work there is simply 40 newton meters. If we take the southward part, again our force is 10 newtons as given, and the distance this time is 3 meters. So we have 30 newton meters of work. Now if we want to add it all up, what do? Well, the tempting thing to do is to treat this as a vector, 5 meters, and say 10 times 5 is 50 joules of work. It doesn't work like that. We take the work done independent of each one another. And since work is a scalar, it is as simple as saying 40 plus 30 equals 70 joules. Okay, I don't want to dwell on this, but go back and look at this and make sure you understand the nuances. Do not make the mistake of just drawing a displacement vector and then multiplying it by 10, because it doesn't work like that. All right, last problem. I got to fit it in the next 2 minutes or a minute. We got a crate pulled across the floor at a constant speed. That's important, okay, and a distance of 2 meters. The applied force is 20 newtons, and the angle it makes with the horizontal is 30 degrees. All right, what's the work done by the applied force? Okay, that's important that we're very specific about which force. So in other words, we want to do this one. So work done by the applied force, of course, is a force times the distance. However, we can't just do 20 times the 2 meters because not all the 20 is in the same direction as the 2 meters. So it shouldn't be hard to figure out that we need a component of the force that is horizontal. So if I draw this in green, I want this component, which is nothing more than F times the cosine of the angle times the particular distance. Okay, so that's the only thing that's different about this. So we would have 20 newtons times the cosine of 30 times 6 meters. I'll leave that to you to work out. I think cosine of 30 is 0.87. So 120 times 0.87 is roughly 100 joules. All right, verify that for yourself. Okay, that concludes this. We'll do more practice in class. you.